One of the most important applications of mutual induction and self-induction takes place in a transformer. A transformer is a device that is used to increase or decrease an AC voltage. For instance, whenever a cordless device, like a cell phone or a computer, is plugged into a wall receptacle to recharge the batteries, a transformer plays a role in reducing the 120-volt AC voltage to a much smaller value. Typically, between 3 and 9 volts are needed to energize batteries. In another example, picture tubes in old television sets need about 15,000 volts to accelerate the electron beam, and a transformer is used to obtain this high voltage from the 120 volts at the wall socket. We start with a rectangular piece of iron that composes the core of a transformer. Iron is ferromagnetic and is easily magnetized. If we wrap one arm of the core with a coil and run a current through it, the current in the coil produces a magnetic field which magnetizes the iron core. The iron not only amplifies the field, but channels the field lines all the way around the core. So the core allows us to position and confine the magnetic field wherever we want. We can now add a second coil, called the secondary coil, to the opposite arm of the transformer. This secondary coil has NS turns, which has a different number of turns than that of the primary coil, which has NP turns. If the current is turned on in the primary coil, the magnetic field lines it produces are amplified and channeled through the secondary coil. Thus, a changing current in the primary coil can cause a changing magnetic flux in the secondary and therefore induce an EMF in the secondary. If a device of some sort is connected to the secondary, which we call the load and is represented by RL, then a current can also be induced in the secondary. What we want to do now is relate the EMF or current applied at the primary coil to what is induced at the secondary coil. From Faraday's law of induction, we know that the EMF at the primary is given by EP equals negative NP times delta phi divided by delta T. Since the field lines are channeled through the core and through the secondary coil, the induced EMF at the secondary is ES equals negative NS times delta phi divided by delta T. Note that the change in flux per unit time through a single loop of the primary coil is equal to the change in flux per unit time through a single loop of the secondary coil. We can get a useful equation by computing the ratio of the EMFs. So we write ES divided by EP equals negative NS times delta phi delta T divided by negative NP divided by delta phi delta T. The negative signs and changes in flux cancel, and we find that ES divided by EP equals NS divided by NP. In a high-quality transformer, the resistances of the coils are negligible, so the magnitudes of the EMFs, ES and EP, are nearly equal to the terminal voltages Vs and Vp across the coils. We can therefore write this equation in terms of the terminal voltages as Vs divided by Vp equals Ns divided by Np. This is called the transformer equation, which states that the ratio of the input voltage at the primary to the output voltage at the secondary is equal to the ratio of the number of windings of the primary to that on the secondary. For instance, if Ns is greater than Np, then Vs is greater than Vp, and the transformer is called a step-up transformer since it steps up the voltage. If Ns is less than Np, then Vs is less than Vp, and the transformer is called a step-down transformer since it steps down the voltage. We also need a relation that involves the currents, and we get this by applying the conservation of energy. We know that, assuming negligible losses, that the electrical energy put into the primary of the transformer must equal the electrical energy put out of the secondary. Since power is energy per unit time, the power in must also equal the power out. We therefore write the power at the primary is equal to the power at the secondary. This means that IPVP equals ISVS, which means that Vs divided by Vp equals Ip divided by Is. And we can now expand our transformer equation to include currents, as Ip divided by Is equals Vs divided by Vp, which equals Ns divided by Np. Note that Vs divided by Vp is equal to the turns ratio Ns divided by Np, while Is divided by Ip is equal to the inverse turns ratio Np divided by Ns. Consequently, a transformer that steps up the voltage simultaneously steps down the current. and a transformer that steps down the voltage steps up the current. However, the power is neither stepped up nor stepped down. Transformers play an important role in the transmission of power between electrical generating plants and the communities they serve. Whenever electricity is transmitted, there is always some loss of power in the transmission lines themselves due to resistive heating. Since the resistance of the wires is proportional to their length, the longer the wires, the greater is the power loss. The resistance of the wires is also inversely proportional to their cross-sectional area, so thicker wires are used to help minimize the power loss. To reduce the loss further, power companies use transformers that step up the voltage to high levels while reducing the current. A smaller current means less power loss, since power equals I squared R, where R is the resistance of the transmission wires. Here we show one common way of transmitting power. The power plant produces a voltage of 12,000 volts. This voltage is then raised to 240,000 volts by a 20-to-1 step-up transformer. The high voltage power is sent over the long-distance transmission line. Upon arrival at the city, the voltage is reduced to about 8,000 volts at a substation using a 1-to-30 step-down transformer. However, before any domestic use, the voltage is further reduced to 240 volts or possibly 120 volts by another step-down transformer that is often mounted on a utility pole. The power is then distributed to consumers.